So interestingly, you see, most slides are behind us. So so I don't know if it's the 15 below there. Right. So, and here also we have like animations. So it's going to be very short. It's surprisingly short. Okay, I don't know. So the first observation is that the problem is easy if G is of constant degree, namely you can solve it in log n space. If G is constant degree and it's an expander. Expander, I mean just, any expander. Omega is smaller than 1. Do you kind of see why is that true? It's kind of related to what I said before about taking a random walk of. Right. Exactly. Exactly. Because the graph is an expander, like omega is bounded over 1, you can actually prove that the diameter of the graph is logarithmic. And so what you can do, you can just say the diameter is like 10 log n, depends on omega, but 10 log n or something. I mean, the path graph, for example, that doesn't have a diameter logarithmic, right? Just to make sure that a graph of size, this graph, which is very bad, like 1 over something, its omega is something like that. It's really close to 1. It's not really good. But once omega is farther away from 1, then the graph is logarithmic in degree. You can actually show that. You will show that because it's related to the other question in the homework. And so this means that, I don't know, there is some number, C, such that in C log n, so the diameter is more C log n. So what you want to do is to just iterate over all possible C log n paths from S. So you need a counter to count the number of steps, and you need also a counter, you're going to have C log n. Okay, let me do the incorrect thing. This is not the right thing to do, but let's see if you can fix it. You're going to have like C log n steps, and you need to remember where you are. So you need log n. Here is where I'm doing something which I can do better. Right. So, but let's see, you can use log n space at which vertex you are, and then in log n square steps you can iterate over all of these things. You need some iterator also, but that doesn't really matter. And if at one of these iterations you got to t, you're happy. Otherwise, you reject. And this is log square of n. So how can I get it to log n?
With a stack with log d space.
Exactly.
Just remember which vertex you are.
Exactly. So the first one is S. It's not even. I don't even have to save it. It's in the input, but I'm just going to copy it anyhow, just for fun. And then I have like log d. I don't have to remember the vertex. It's just the neighbor of the neighbor number. So in log d, so d should be constant if you want to get something. But if it's slightly subconstant, it's also nice. But if it's constant, then the space usage is something like this. So it's order of log n, and you're happy. But no one gave you such a graph. Someone gave you this graph, maybe. Well, if they give you this graph, you knew it's connected. But maybe there is an edge missing. So what can you do when someone gives you something you don't want?
Approximate or like expand it or something.
Yeah, good. Yeah, make it what you want, slowly but surely. So what we are going to do, and we are going to do it carefully, is to transform the given graph G, and the transform is like the essence of the thing. How do we transform? But the given graph to a constant degree expander G prime, but not ignoring G. So we are going to respect the connectivity. So two vertices are connected in G, if and only if I want to say the same two vertices are connected to G prime. That's not going to happen because G prime is going to have other vertices. But for the two vertices in G, there are going to be two corresponding vertices in G prime, such that if the original vertices are connected, then so are the other. That's what's going to happen. So G prime is going to be slightly larger. Actually, it's kind of annoying.
Like if and only.
Yes, if and only if, exactly. So we are going to maintain up to the fact that the vertices are changing. We're going to maintain the connected components. But you will see exactly. But that's the strategy. And the point is, we do want G prime to be an expander and of low degree, right? Because of the previous thing here. We want low degree because otherwise log d will increase, and an expander so that log n some constant number of steps will reach any vertex. So we want a constant. So we don't want G prime to be some expander. We want to be a constant degree expander, which is a constant degree which is an expander, constant degree expander. So what we are going to do is we are going to use squaring and zigzag, not for the purpose of constructing an expander from scratch, but for the purpose of transforming G to an expander. So that's where, I think it's a it's a killer application of these operations, because you don't just use them to construct something that people knew how to construct.
G is
No, undirected. No one knows how to do it for directed.
Potentially happen is that every connected component becomes expander, right?
Right, exactly.
S&P
Right.
connected
Sorry, yes. Right, I said that G prime will be an expander. It's not going to happen. If G is that's the point. If G is disconnected, if G is disconnected, G prime will be disconnected by what I said. What I meant is that every connected component will become an expander. Thanks. Yeah. I contradicted myself.
G was connected.
Right. We'll output yes. Right. We're trying to figure out essentially whether this is the case. Good. And so we are going to obtain this G prime by applying squaring and using zigzag. So squaring for improving the expansion and zigzag for reducing the degree, as before, really. Before we did that to construct a graph from a small graph, but here we are going to make sure, we are going to do it in order to transform a graph to such that every connected component is an expander. Questions? Thanks for the remark. Okay, so let's see the algorithm. It's
Learning the graph of because every step is by a constant.
right. So it's a polynomial factor. It's polynomial factor, yes, but that's fine because the log of poly n is a log n. But yeah, we'll see. Okay, so okay, I just wasn't sure if this is the second one, right? Okay, we're good times. If it was the third, okay. So we are given an undirected graph on n vertices and 2 vertices, right? So that's fine. And when you are saying we are given an undirected graph, what I really mean, maybe let's specify, we are given an algorithm that computes if it's deregular, I could have said that, but I can't say that. That computes the edge rotation map. So when you're given a graph, it will be nicest to work with the edge rotation maps. Okay, but the graph is not deregular, so I can't really write what I just wrote. So what I should write is like something like that, and it doesn't really matter. So the degree could be anything, and if you go above the degree of a vertex, you put an abort or something. And this is my notation for output is the same as the input, like type. Output type is the same as the input type. It doesn't stick, but if you have a function, right, from V to V or something, I don't know why I'm not writing it down. Just save space. But no one. This has a meaning?
No, just the.
But in this context?
No.
Yeah, exactly. So yeah, I could also write V to V to save space or something. Yeah, anyhow, so when you're, let me just remove those. So when you are given a graph, when I say you are given a graph, I mean there is a way to compute the rotation map. Regardless how someone would give you the map, you can find a way to do that. It's not an assumption on the graph. It's just our agreement of how we work together. And the ingredients will be somewhat similar to before. There's going to be a graph which is deregular. These any number for which there is such a graph. I don't really mind, but think of 100 or something. But it also returns right, the J. Right. So H, we are going to have this gadget H. That's be in the zigzag. It's going to be a deregular. This is a parameter doesn't exist yet. There is a parameter that I'm introducing. Deregular is some constant. I need to be, some spectral expander. So 1/4 is nice, spectral expander. on D to the 4 vertices, and for an annoying reason, I needed to have a self loop, one self loop on every vertex. Okay? I don't want it to be bipartite. That's the way to do it. It's a cheat, right? It's like because there are even cycles. Actually, here you can just, if you want, it's weird, but you can choose one vertex and put on it. It won't be regular anymore. I don't mind, but let's just put one self loop on every vertex in H. Now the first step, even though it takes a lot of space, like in the slide, is kind of trivial. It's just for convenience. So in the first step, I just want to make sure that G is regular. That's what I want. And it's an old trick to do that. I want it to be regular, and again, I want to maintain the connected components. So the trick to do that, there are words written here, but let me just draw a picture. Oh, ignore this, I'm just using this for us. So say you have a graph which is not regular. It's a general trick that people use in combinatorics to say that it's enough to prove things for a free regular graph. It's a known exercise in problem sets. So say you have a graph like that, and you somehow want to construct a free regular graph from this graph, which has the same connected component structure, say. So maybe there are other things here, I don't know. Then what you can do is you can just replace every vertex by a cycle. So I can put, you can do it in log space also. So I'm going to kind of, every vertex is connected by a, so you see, so this, so maybe I should draw a smaller picture so I can actually do it. But yeah, maybe just have some neighbors here so it won't be annoying. Yeah, like that. So we are going to do it like that. It's a proofing picture.
So we put like each.
Right. It's kind of a. It's kind of a replacement of the line graph with the cycle. What you really do is, you take every edge, on every edge you put two new vertices, one closer to one vertex and one closest to the other. Okay, so you have like these vertices. So every edge you have two vertices now. The graph increased a little bit, and for every vertex you connect by a cycle all the vertices close to it, right? On the edges, close to it. Maybe yes. Right, leaves are like that, and then for example, this edge from that, because of that vertex, you have this cycle, free cycle, and then you put an edge, or you can do it before. You put an edge between the two vertices you put on an edge. Right. So really, what happens? Every edge that occurs in the graph induces two new vertices. They are connected, and this vertex is not only connected to that vertex, but also to the vertices that you put on the close part of the edges of the edges leaving that vertex.
Except for edges to connect
No, I think it's fine. So if you have a leaf, okay, so for example, this leaf,
it's not
at most.
You can just
if you want regularity, you can do self-loop or something. Maybe, yeah. But I mean, they get most of it. Yeah, good. But you see what happened? I just kind of replaced every edge. You can probably write it as an operation, but I'm just saying it. You can add two vertices on every edge, so the graph increased, but not by much. And you have put an edge between the two vertices on the same edge. And so that's one thing. But then, for maintaining the actual connectivity of the graph, you put a cycle on the vertices that are close, new vertices that are close to a vertex, to the original vertex. Easier.
But if you really don't mind self loops and you don't mind the fact that the leaves are probably, why don't you do the same thing for the original graph? Just take the graph.
I want the graph to be at most regular, for example.
But you wanted constant.
Right. Because it just because in the zigzag I need a constant size graph, but I do rather it to be regular actually. I mean I don't have to, but it's nicer. So let's also put something.
But it's not the constant rather than the regular.
Right. Yes. Exactly. Because otherwise, you can just you take the highest degree, put some loops. Exactly. Yes. But you want the graph to be small because, right, you will see because the space depends on the graph size. Good. So that's just a way to transform a graph to a free regular graph here, which maintains connectivity. But again, what do I mean connectivity? So if you want to know whether there is an edge between two vertices, you can just take any of the vertices, new vertices that are close to it. So it's not exactly the vertices that you have, but it's the same thing. You replace the star with a cycle. This, by the way, is a worse expander than you started with, probably. But it doesn't really matter. If you start with an expander, this is not a great expander usually. I mean, at least if you use the bounds, so good. So that's the first step. And actually, I don't want it to be free regular. I just said I want it to be free, but I want it to be d squared regular for a parameter d. Now, d is 100 or something. I don't mind what d is. I just want a d regular graph, which is 1/4 spectral expander. So d cannot be like 2 or 3 or 4. It has to be just 50 or something. I don't know what's the number. You should compute 2 to the square root of d minus 1 and check what you get for this to be over d to be 1/4. So think of d as a constant. I want to use the zigzag with this graph. It's on the d to the 4 vertices. So I want the graph to be d square regular, and you can do the trick I did and add many self loops. Okay, if you want. If you want to be smarter about it, you can do other stuff, but it doesn't really matter. I just want the graph to be regular. That's not really important. But importantly, I do it in a way such that S and T are connected in G, even only if some representatives are connected in G0. And so solving connectivity in GST is the same as solving connectivity in G0 S0 T0. And note that I'm assuming I'm doing kind of log space computation here. Like there is a way. You need to transform things. That does require log n space because the degrees could be of size m. So here there is an underlying kind of level of that we kind of ignore from now on that takes log n space, additionally log n space. And the important part is actually step 2. So in step 2, we are going to run for some number of iterations. Let's call it L. It's some constant time log n. It's a constant that you can figure out. And when you code this, you should figure this out. But there exists some constant that depends on this 1/4 and actually and that's it. And on the constant you get from the homework, but it's the same thing. And what you do is the following. But think of it as log n. So you're going to kind of forget about the implementation space-wise. We are going to define the graph GK to be as the way we define it when you constructed expand the first time. So GK minus 1 squared zigzag with H, no tensoring. Okay, we know that this will become a better expander because we proved that. And then we are going to define SK and TK to be any two vertices in the clouds of GK corresponding to the vertices you kind of started with. So what do I mean? GK minus 1, it's a graph. You have SK minus 1 and TK minus 1 sitting in clouds. So like these are the clouds. Right, so SK minus 1 and TK minus 1 are vertices in GK minus 1. So when you square, nothing happens to the vertices, but when you zigzag, the vertices kind of goes away and become a cloud. And the actual vertices are now sitting like here. They are like, I just moved. They are like d to the h is d to the 4 inside. So the d to the 4th vertices in every cloud. And I don't know if there is I really don't know if there is a path from SK minus 1 to TK minus 1. That's what I'm trying to understand. But anyhow, I'm going to call this SK, just choose one of them, and call this TK, and that's how I defined SK and TK. Okay, SK and TK are just some vertices in the clouds of GK corresponding to SK minus 1, TK minus 1. And kind of going to repeat this. And after logging iterations, I'm going to do what we did in the solution where we assumed that G is an expander. I'm going to go over all order of log n length path in GL. This constant is actually interesting. There is a constant related to the graph size, but GL actually is, as we said, it has a size which is larger than the size of G. It always multiplied by d to the fourth, but this is constant, so it's going to be like poly n in the end, because there are log n iterations. D to the fourth, and you raise it to the power to the L, it's like poly n. So this is not the usual n, it's like the poly n that you got, but the O, the log n and the O, you don't see those. You don't see those at a high level, but it's hidden under this constant here. And so you're taking a path of this length. The graph is a constant, has constant regularity. It's this regular, I think. Yes, it's this regular because of this H. And you just check whether there is a path from SL to TL. And forget about space. That will be after the break. But you know that there is going to be a path between SL and TL, if and only if there is a path between S and T in the region. So, and that you can do in space, which is order of log n. So this you can do in space log n. This you can do in sub log n. This is unclear. This you have log n iterations, and unless you're doing something right, right, exactly. So if you're going to do that in the naive way, that's going to cost log n squared, log square of n. Right, that's what I'm going to do, but it's not trivial. There is a way to do it, what you might call in place to do these things, and that's what we'll do after the break. But that turns out to cost log n space rather than log square of n, and so forth, and therefore everything works in log n space. And we're happy. So let's meet after the break and we'll do that. So let's continue. Good, so we are just about to analyze the space complexity of this algorithm. And really the only thing we really care about is this part. Yeah, right. But that's the same thing as we did before. I should just say that omega of GL is constant. Like, it's the same calculation that we did before, essentially. Right, I want to show that the last graph is an expander. The only difference is that before we knew the expansion of the original graph, we took the graph by ourselves. And here, when you start with a graph G, you don't know its expansion. So the only non-trivial part here is left for you in the problem set. It's not hard, but it's to prove that a gamma, like 1 minus omega, cannot be too small. Okay.
Wait, what is it? Gamma
C0 is the origin. It's the original. It's okay. Good. It's what Gal said. It's a connected component containing any vertex in the original graph or the first graph that you start with.
before after the trick?
Right. Good. I was wondering. So it doesn't matter of any undirected graph. So you start with an undirected graph, and you may or may not do that to it, but you end with an undirected graph. And what I'm saying is that every connected component, so let's call it C0, it's the initial one. It's not an expander, but it's not that terribly expanding. So gamma is at least 1 over poly n. Right, gamma is 0 when it's disconnected, because it's 1 minus omega, or bipartite, it's 1 minus omega. What I'm saying is that if you have a graph which is connected and non-bipartite, so the distance from 1 is at least 1 over poly n. N is the graph size, or the component size. Why is this
It could be any graph?
connected in a non-bipartite? Yes.
Oh, it's not. Okay.
Right.
Not
So what I'm saying is that in undirected graphs, once omega is not 1, there is like it's kind of, it cannot be, it's not too refined. There cannot be like a 1 over exponential n. Once it's not 1, it's farther away by 1 over poly n. That's really just because, well, I just, here's the problem. Gamma is 1 minus omega.
okay.
Right, that's what it is. And that's it, really. Once you know that, you're fine. Because we know that omega of a graph, so the CKs are like the connected component in GK containing the vertex. This is the way. So as Gal said, we defined actually the operation on the graph, but if you think about it for a second, it's the same as applying the operation for every connected component, because they don't touch things that you cannot touch. And then you know that omega squares, and you know that, so here I need the stronger bound. You know that gamma, there was the omega bound and the gamma bound. Right? Remember I told you this is a stronger bound than the bound that we started with the omegas. And kind of that's what I'm using here. So I know that omega of ck minus 1 squared is the square of the omega ck minus 1. And if you think about it in terms of gammas, this is what happens. Before the zigzagging or something, just replacing omegas by gammas. Can you see that? You can see like you do a 1 minus. It's not hard. 1 minus here, 1 minus here, and you complete a square, and it's the same thing. And so gamma of ck is, you know, gamma of this thing, because this is ck, and this is gamma of h. Omega was 1/4, so gamma is 3/4. You square it, and this is gamma of this graph. And if you use Desmos, you can show that you know this is usually kind of increasing. So when gamma is small, you start small, maybe it keeps increasing by some constant larger than 1, gets multiplied and multiplied up to some point, at which case it's not getting larger anymore, but it's not getting smaller ever. Right, so what happens here when gamma is very small? This is negligible. If you think about it, without Desmosing, this is negligible, and this is like larger than 1, because it's 18/16, or something, right? 9 squared over 4 squared times 2. Right? So what happens when gamma is not too large? When it's small and this is negligible, you increase gamma by a constant factor. But at some point, that's that's more daunting when it helps, when this helps or something. When this time that helps, and the sweet spot is it's actually not this number exactly, but it's a clean number to write. So 1/18. So essentially, what I'm saying is that gamma of ck it's always at least 1/18, and when it's small, it actually increases. So if you look at it for a while, if you apply it for some constant times log n iterations, because you start from 1/poly n, every time it gets a hit by this. So this to some constant time log n. So at some point it will go over 1/18. So and it will stay at least 1/18.
It's greater or equal, or less equal, because here in the gamma, like it's.
You want gamma to be large. You want.
I mean, like the gamma is bounded.
Sorry, this one. Yes. You're definitely right. That's really bad to have. Yes, gamma should be large. Omega should be small. Yes. Okay. Good. So that's not the interesting part. The interesting part is the space complexity, because it's the same as what we did. What I just said when we constructed the zigzag graph. Okay, so let's spell out what we want. So what we want is to ask what's the space complexity of computing this function, namely the edge rotation map of GK, from like what's the overhead of in space for computing that, given that you compute that. So how much more space do you need on top of the space required to compute the edge rotation of GK minus 1 if you want to compute the edge rotation of GK? Where I remind you that GK is as before. Where is it here? Right, so this is GK. You square GK minus 1 zigzag with edge. So you do 2 operations of that and do a zigzag. Right, that's the question. So given a function that does that for you, how much more cells of space do you need on top of that? So you allocate whatever it needs, but on top of that, how much more do you need in order to do that? Log n is trivial because you can kind of everything is of size n here also. This is even constant. And you can always, like, with log n space, you can have like one more walk tape, really. You can simulate one more walk tape and just do it, like, irrespectively of each other and just combine the results. But I want to do it with a constant overhead. All right, so we're going to do it slowly, but I just want to make sure I understand. Someone knows how to implement this function, given an input in some space, and I'm asking you, you can call this function twice, you will call it twice. How much space do you need extra on top of the things you allocate for that in order to compute this? It's not clear it's constant. Yes.
Wait, but what we actually do, we don't really do the function, we do the function on the specific value, right?
Right, yes. Right, yeah. So someone give you on the input tape, here's a vertex, and again, a vertex here is like a cloud of a vertex, and 2 elements in D. The square should be here. I wrote it in the morning. It doesn't really matter, of course. But
edges for the squaring.
Yes.
And then for the zigzag, some other vertex edges.
Right. So let's do it. You're right. There are 2 slides, one for each of the things you said. But I just want to make sure I understand, because what we're doing, we're computing this function given an input, using that function, and extra, hopefully constant number of space cells. Good. So again, I warned you of that. So that's the same as what we had before. It's kind of model dependent. You can do it model independent using log n space, but it's not. It's model dependent. So I'm going to do it very carefully. The end result is not model dependent, by the way. Just kind of the inner working of this thing, which you have to be worried about. Otherwise, it's okay. And the main claim, it's actually, I don't know. The main theorem is that the space for computing, right, so we know that GK, as you said, there are 2 operations here. And we will just analyze each. So it will be enough to show that, and this is kind of a, I don't know, informal statement. The space required for computing G squared, or rather pi of G squared, is, I can show, it's the space for computing G, it's like 1 times, right? Exactly, the space for computing G plus a constant. A constant here would be a killer, right? It should be 1. Smaller than 1, it's impossible. And the space for computing that is also, you can do it with additional constant overhead. And together they tell you that you can do that with constant overhead. Right? Because you can just, you should be careful, but things should talk nicely to each other, but okay. So when I say that you can compose them, actually every composition theorem in space requires log n space, unless we are all very careful to clean the board and make sure we understand each other before we're leaving the room. Like we should be like think on how we leave the input and out, but we will do that. Everything will be clear for us and for the algorithms. The cells will be clear. Okay. So let's see. Let's do the. So again, I wrote this in the morning. So let's see what happened, because I didn't really like the slides that were there before. So here I'm going to do the space analysis for the square, and then we'll do it. I wrote it and then decided it would be actually better to do it together. So let's do the square first, okay? So what's written here? So again, given our edge rotation map of G, and forget about the general context, there's the VK and so forth. Just a graph, D regular on vertex at V. Given an edge rotation map for G, I want to be able to compute the edge rotation map for G squared with constant overhead. And note that I'm writing D squared here. Maybe it would be better to write D squared here. Does it really matter? I don't know. I think of it as 2 elements of D other than element.
As a graph.
You mean you rather to say it like that or something? Like
no, it's just like as a graph. You don't have.
you can store your you can, it's okay. It doesn't really matter, but you can index your the neighbor of a vertex not just by numbers. Right? You can do it by pairs. Right. Yes, and then you get this notation. Right. But it's fine. I mean, once you fix your notation, it's fine. And for the log space algorithm, it doesn't really matter because you will anyhow put them like that. So you put it in log d bits and then log d bits anyhow. So let's see. So let's see what we're trying to do. We'll do it here, but let's just, the math of it is that, pi g squared gets a vertex as input and two numbers between 1 and d. So this is the vertex, and these are two numbers between 1 and d. So you can think of it as number in d squared, but I rather think of it like that. And maybe you want to put parentheses here, or maybe a semicolon or something, just to separate more explicitly the vertex from the neighbor number. But and what you want to output is what you want to output. So what do you want to output? So how does squaring work? So you start at vertex v and go to neighbor I of v. You get to some w. Pi g will tell you where you go. You go to some w, and w considers v as its I prime neighbor. Good. And then from w, using j, the second coordinate, second the number between 1 and d, you move using pi g to u. And pi g also tells you that j prime is the way to go back. So with this picture, what you want to output is u, j prime, I prime. Not I prime, j prime. J prime, I prime. Because you want to return like that. At some point it matters actually. Because if it's long, you have to go far away. You want to read it like that, not right? Because the weight from u to v is like that, and two indices are fine, but if there are many of those, you can't just flip them in constant space. Right? You should be very careful here. You should do it like very locally. Exactly. Yeah, constant log space computation. So let's do this. So this is like the math of it. Let's do it in space. Like so this is the workspace. Okay. Now, as I said, here we don't have. I mean, it's kind of confusing here. This is the workspace, but we are working in place. So in the workspace, we are also given the input to the function. It's kind of breaking the rules a little. Okay. And the agreement between all functions is that the head is always at the end of the input. What will happen is that here you will have a lot of information that you don't want to erase, but it's not relevant for your current thing. So the location of the head, which you cannot store, it should just be there. You should always clean the board before you move, before you leave the room. So when you want to ask pi g a question, you should write the question, pi g square here, you should write a question and put it at the end. Okay? Things appear here as well, but not for you to read right now. What is what? Sorry?
What is written after the J?
Who knows? Like depending things you don't want to erase. Like you will see in the what's going to happen, things are going to be read there, to be written there, and you are a subcomputation that are doing something here, and that will affect what's going on there. So here it's not empty or something, but what I'm saying now is that I want to evaluate pi g squared at Vij, and the assumption is that I'm working in place. Vi and j are written at the beginning. That's always the case. The head is at the end of the input to whatever I want to ask. And here I cannot write things here. There are things here that should be stay there because someone will use them later. It recursively called me and put some information there. It put the question for me here. I should work here and leave these alone. That's kind of in place computation. So that's gold. You shouldn't touch this. I don't have gold. You should touch gold. Okay. So so what do you want to do? So you have the head here. By the way, this is long. You don't have the space to go all the way here. By the way, just think about it. It's crazy, because if you want to go, it's like a journey for you. It's like log n bits required to specify the vertex. You don't have the memory to remember log n bits. You can do it with log n, by the way, but you don't have the memory to have log n bits. And interestingly, at the same time that Omer published his paper, a student published log n. result. I put in SL in L times log L, which is roughly because of what I said here, and that's a shame because it was amazing paper, but you know, and so he won the best student paper, and Omer won the best paper, obviously, and then the student retired like after the PhD, just moved away from the field. So Omer could have done actually more damage than good for the anyhow. Right, maybe he's doing like cancer treatment, and Omer did more good than who knows, right? Yes. So store V, but not to transverse it. I mean, this is log n bits, and if I want to move my head and know where I am, like to count track of where I am, I need log n bits.
Where is the extra space that we're using?
Good. That's the question I want to ask you. So I'm going to do that. It's actually related to that. So I'll just tell you, it's the head movement. I'm going to say, move the head here. How do you know where to stop, when to stop? So what you need is to remember how many steps you did. Right? And so the extra space, there's going to be another extra space. You can put another extra, you should have another extra space somewhere. That extra tape, yeah, that allows you to just do the head movement calculation. Which you can ignore. I mean, initially you kind of ignore this overhead at all. It's like zero space. Just move the head. Like, move the head. Come on, what's wrong with just moving the head? But you know, you need to do that, and then you need to, and you can't remember where you are. You just remember the shift from where you are. That's
the idea is that it only depends on D.
Right. Exactly, and that's another reason why the degree bound is important. It's also important for stage 3 at the end, but also for that stage. Again, it would be log n log n. It's still an amazing result, but because you can move all the way from V in log n space. But you know, so let's see what we do. So I want, first of all, you know, looking at this function, or actually looking at this picture, I want to call pi of g to figure out, you know, given V and I, who is W, and I prime, but who is W. So what I need to do is to move this little thing here, because the agreement we have is that that's how I give you the input. And so you see J is here, J is sitting here. Pi G shouldn't touch that because I need it later. So pi G squared calls pi G on this input, because the agreement is that the input is from the beginning to the right arrow, to the red arrow. So J shouldn't be touched because I need it later. So I move it here. That requires O of this space, no of the, O of one space depending on the, actually log this space, but some number depending on this space. And then I'm using, so in that tape, the same, I'm using this space. I can reuse the space. But anyhow, that's not, no, sorry, I'm not using space. I'm using that space, and I'm using this allocated space. I am allocated space of pi G space to begin with. I'm just asking on top of it how much do I need to compute W and I prime. W and I prime. And again, the agreement is that once you finish the computation, you put the head back to the end. You see, it's really pedantic. You have to do that. You can't put it here because it actually, if you put it here, it won't be here because recursively it will end up here someplace. So you just keep doing that. So you put it here. And now, given, so I prime is fine, W is prime. Now I want to compute pi of G on W and J. But I don't have J here. I have J here and I prime here. So what should I do? Exactly. Exactly. So I need a little algorithm that swaps these two values bit by bit. You can imagine this. It requires, maybe you can do it in linear space in number of bits here. I can do it in quadratic space, but it doesn't really matter. Probably you can do it better. I don't know. I'm not sure. Maybe you can. I don't know. Doesn't really matter. It seems like you have to go a lot of times, but it's still a quadratic in constant, so it's fine. It's actually quadratic in the log of a constant. Naive?
No, like the times.
Right. Right. Sorry, that's the time, not the space. Right, that's fine. That's fine actually. It's log. If it's log square of something, it's still log. Right, it does the space, not the time. Yes.
I was thinking that because for the computation, you don't actually need it like reason in whole. Like you can actually compute W on the go, like when it's like beat.
That's what will happen actually, because it's recursive. Yeah. Right. That's what's happening. But I'm just showing like one level of recursion. But if you think about it, W is not W. It's a Vij of someone else. So there's also the zigzag. Yeah, exactly. So when you do space, that's important. You write the algorithm like that, but because that's no one will read this. But you have to, on your board, in your office or whatever, do this and make sure that you can do it in the space you're saying. Because when you write an algorithm, you don't say anything about the implementation, and that's what happened here. Who is you in? I mean, it's recursive. Okay, so we flipped I prime and j. So we are here again. It's constant space, and now we have kind of double, and we also put the head here, and now we have W and J ready for another PyG call in the same space, right? Not twice. Unlike the time analysis, which forced us to consider the tensoring also, because the recursion was kind of longer. It's not, we're not multiplying, the time will multiply by 2, but not the space. We can reuse space. It's like a dip. Okay? You don't reuse time. You live once, but space you can reuse. And you do that, and instead of W and J, you will get in this picture U and J prime. And that's, I mean, you're happy, except for one little thing. Very good. You need to do this. Because if you forget, everyone will forget, because it's the same algorithm. And that's it. That's how you do that. Yes.
So, I guess what I understood when you say compute like the J prime, basically like move to a state that computes it for G or G T. But in order to do that, we need space for that machine, like for that logical function.
Yes.
So
space for PyG, you mean, or for computing GT minus 1?
Like when you have WJ, do a single step and say, okay, now we have UJ tag, J prime.
Yeah.
Like someone did this for us. And my understanding, like formalize it with the full machine, is that we go to another state that perform this.
No, not state. So, right. No, it's not state. It's like, what you're saying is that we need to remember T. Right. Because
what we need to remember T, we also need like information about like GT.
Yeah, so, but okay, so in what I'm saying now is given this information, how you can do G squared. Right? So
even before this would be G squared, but
given G.
But where is G? Like G,
there is G0, which I assumed you're given as pi also, kind of remarkable.
Yeah, but like
there is no
like only what's in the tape is the
like there is one input tape containing G0, and pi G is used like that's the original G. It's actually using that input tape to do stuff.
That's fine. But GT should be somewhere on the tape.
It's like, yeah.
You cannot have GT. If you have GT, you
exactly. It's like a ghost. It's like every time you want to ask a question about GT, it triggers a sequence of questions going all the way down to G. And then you get G0, sorry, and then you get the answer.
Like some formality is missing. Like, okay, so we want to complete that.
Right. So maybe this is G is G, and then this is G squared, like G0, and this is G squared. That's the base. No recursion. Like, when you see I'm doing this order of one calculation, when I'm calling the algorithm pi of G0, it replaces here, like inline in space, the input with the output.
G0?
So there is, so G0 sits in the input tape, and pi G0 it operates in log n space. It's not have to be constant space. It operates in log n space. It's really easy to do it in log n space.
Yeah, you get this in the input.
Right.
I'm just trying to formalize out of the GT, like the step calculated.
So I broke it down. It's confusing, but it's the only way to kind of do it. G squared and zigzag. And then it's a sequence of operations like that. So when you want to ask in GT who's the ith neighbor, when that again triggers like many questions, go down all the way at some point, many times, pi G0 will be called. Maybe, I don't know.
I think it's some additional information is needed on the tape. Like if we're on the T step, we can possibly only use like a constant amount of
no, there's the OD one space that's based on a different thing.
Yes. Yes. It's not here. You cannot put it here. It's another walk tape.
We have T small walk tape.
You can do that, or okay. I just imagine that there is like one and everyone keeps using it. But yeah, maybe.
That's also fine.
Yeah.
I can get
Okay.
reduction from
more
depth to one.
I don't know because there are log n tapes. Maybe you can because the whole thing is log n space. Yeah, probably you can. Yeah. Right. Yeah, I'm just worried.
Just put the basic, like, there you go with the,
Right, and you know how much each they need it, like they need it in their own place. So like GT everything's like ordered. GT doesn't call GT over 2, just T minus 1. So they use the space like you can do it in the one tape or in several tapes. That's fine. Okay. So let's do the zigzag. There is one thing, and the only reason I'm just hesitating for a second is that I'm not sure why I need the reversibility here. So maybe to go back in the recursion. So right, because I can't go back otherwise. So you see, given you now I can apply it backward because I kept J prime. I mean, why do I use J primes? Right, that's the question I'm asking. Why? I just want to know who vertex I can. But given this information, I can go back here because I'm just plugged the. But I can't seem to manage to see why do I need that. Can you see that?
Otherwise, like stack. You want to go
Right, exactly. There is no stack. I don't want to have a stack that contains my information. And then when I unstack here, I reveal the information before. So it's like in place like that. When you go back in the recursion, you can actually, you do that backwards. Good, yeah, good. It's confusing because you're used to a stack. When you do recursion, there is like an operating system that does that for you, but not now. Now you are doing it for your own because there is no stack. You can't have a log n stack here. Okay, but that's maybe we should talk about it, but I do want to do the zigzag. So let's do the zigzag first. So in the zigzag, it operates kind of the same. It will be the same, but it's nicer. So you are given pi g and pi h. Forget about gk and so forth. Just pi g and pi h, and g has vertex at v and it's deregular, and h is deregular, of course, because otherwise you cannot zigzag. I don't look at the square. I just look at g and degree c, some degree c. And what I want to compute is this edge rotation map of the zigzag, which now notes that the vertices are vertex time degree or vertex time vertex. That's the better way, like a city and a neighborhood. Right, that's the cloud name and that's the neighbor inside it, like here v and I. And the degree is actually, the degree is actually c times c. I told you I wrote it today. So the degree of the zigzag graph is the square of the degree of the small graph. Right? D times C is something else. It's like the randomized squaring. Never mind. So that's just the types. And let's just make sure we understand it. So pi g of h gets a vertex. So that's V and I. And it gets two like instructions, A and B. two elements in the set 1 to C. So this is like the vertex. You see it, it's here. And this is the instructions, like where to go. And what you want to output, well, again, set notation, so let's just do it. Say that this vertex, Vi, so CTV neighborhood I, its eighth edge, its eighth neighbor. So eighth neighbor of I in H is A prime, and going back is I prime, and going back you go back with A prime. Right, so I and J are going to be the neighbor's name, and A and A prime are even smaller, the instructions within H. So the eighth neighbor of I in H, regardless of it, is I prime, and going back you go back with A prime. And then you do we don't need instruction, just do this step, the unique step you can do in G, namely the I prime vertex neighbor of V is U, and you go back using J prime. And then use the second instruction B to go in H with respect to the graph H from J prime to J. So J is the Bth neighbor of J prime, and the way to go back is using B prime.
Yes. On the last question, I don't think you need to do like reverse calculations, but you do need it for the zigzag, because the zigzag requires you to know where you pin for like J tag is the jump from I tag to J tag requires knowing which neighbor, right?
That's definitely no. You don't need A prime here.
Like in the algorithm, zigzag, you need the.
I don't need to go. I don't really need that. I think it's for the recursion. It's for the because when you go back in the recursion, you want things. When you recurse, you want when things go back, you want to have the same input. So you need when you go back. Usually, it's the stack that contains the information that you need.
But you assume you have the result, and you don't need to those stuff. Never mind.
Yeah, let's talk about it afterwards. I mean, I think it's for that, but it's not clear in my head. I mean, I understand why it's a way to do it, but yeah, let me just postpone it.
How is it now with the regular stack? Like what the standard is?
There is no other information than what's written here in this space. So the stack.
We have instead of we have like T small.
Yeah, log n. Yeah, T.
Yeah.
Yeah.
And each one has the constant table of F.
Right. So that's for that, but not for storing like what on the stack. What you want to put more than that? Other things or?
No, I'm saying it's exactly like stack. And then just go back to the caller.
Only I is a stack, but space by G is not stack. It's simply.
Yeah, sure.
Yeah, but that's fine, right? Because that's what you want to have at the end.
Yeah, that's why I said that I don't. That's the reason.
Yeah, good. That's what confuses me as well.
No, I think you need it for the thing that
No, I don't think you need it. I don't think you need that. If you just want to know who is the eighth B neighbor of Vi, you don't have to use A prime and B prime for that. I didn't use them. Okay, let's see. I'm confused. But let's do that still. I mean, just so we can do it. I mean, if we don't need it, we don't need it. I don't know. Yeah, I'm just thinking about it while I'm talking. I know where you did it. When at the last step, in the third step. I think in the third step you need it. Right, when here. If you exhaustively search and things will change things to you. Right. So for computing one thing it's fine, but when you want to iterate, you want to iterate. You need the same thing to be there. Because otherwise, what are you iterating? You do one thing and then it's changed completely and you don't see what. So when you iterate, you need to iterate. You need to increase this by one, then this by one, so forth. And if you do that once and everything changes, it's not iterations anymore. Like you iterate over kind of a common space. So if you increase by one and everything changes because you asked a question, then you cannot iterate like that because everyone keep messing with your iterations. So you increase by 1, things change. You need the answer. Did I get to that vertex or not? And you change it back. See what I mean? So
yeah, one table.
like remember everything, put it in there.
Just the number of each part.
Maybe.
So
Okay, let's see. That's a good point, but I want to let's do that because now we're really out of time. So okay, so let's see what we have on the tape. It's kind of the same. So you're given V and I, that's the vertex name, and A and B, and you put the head here, and then you start, right? So what do you want to do? First thing? Right. So you kind of want to ask H, who is the 8th neighbor of I? Right, so the first thing you need to do, let's do it like online. You move it here. I don't know if it's good because then you will have nothing left to see afterwards. So actually, maybe that will prove us you need to. Right. So anyhow, let's not. Okay. Now I said initially, but actually that was wrong. That the assumption is that the input starts at the beginning.
just at the end of what.
Right, exactly. You know this length. Like pi h know this length. So yeah, my bad. So now you call pi h on this. Pi h is constant. It's not recursive. You call pi h on this thing, and that will be replaced by right I prime and A prime, because that's what it does. So actually, that's easy. I prime and A prime, and what will happen to the head because it's nice? The same place, fine. It will move, but in the same place. Good. Good. And now what you want to do? No, I think.
You want to exclude the H, the G.
Right, you want to do the G, right? You want to ask who is the I prime neighbor of V first. You want to move here. Right, because you want now we want to compute pi G of V I prime.
And then go to the edge.
Exactly. So let me do that. So you move the head. Let me maybe do two things. Let's do like that. I move the head here because it will take too much time to do. So now it's here. That's constant. And then I call pi G here. So this is pi G. This is pi H. This is moving. This is also moving. But
Yes.
Yeah. And when you do pi G, V becomes U and I prime becomes J prime. V becomes U because that's where I'm heading. Actually, it's nice that you can actually. It's actually better when just erasing. Yeah. Good. Now we are here. And we want to compute what? The B instruction. So we need to swap again A prime and B, and which is also good because we want it to be at the end. For some reason we don't get, but we should get. So let me just remove this, move that here, J prime, switch. I want to switch. So I'm going to put it here and switch. So I'm actually switch and then put it here. Because now it's ready for a call, for this call, to the H call. No space, it's kind of ironic. Yeah, so let's squeeze this. I wish you could do it in like space, really. But anyhow, when you do that, you get so I'm moving using H from right. So it's going to be J without the prime and B prime. And then at the last step, I'm just going to, excuse me, just move the head, and they're happy. Because I see U, J, B prime, A prime, U, J, B prime. Okay, so now we have like a couple of minutes. How do you reconcile this thing? Do you need?
Yeah, Yeah, because we use JSON, right? We use JSON.
I use JTAG, you're right. You're completely right. So the idea here was that you, for the zigzag, unlike for the scrolling, right? If I'm not mistaken, for the zigzag you're actually using the primes. So you need to have them there. You can't just not compute them. Right? Sorry, did I use by H twice? So right, so right, I should write it. Yeah, that the move is not really important. This is right, yeah. Right, yeah, that does make sense. And you're right. You're completely right.
No, but J prime is an H. It's not something in the recursive.
But it's a prime. No, but it.
It's the recursive, but you need to know what J prime is from the recursive.
No, but everything is recursive. So now you go to U, things are recursive here.
This is recursive, but J prime. Oh yes, this. J prime.
A lot is for I to I prime, and that's why J prime and then J. Or J prime and then. When you calculate by H, you use
From J prime. Who is the beef neighbor of J prime?
Yeah. Yeah, but afterwards.
No, the question was why do we even put them there? I mean, there is no afterwards because that's everything is like recursive. If you don't put it here and you go your journey in computing U, because U is not a U, it's actually also when you get back to this point, you won't have J prime to go to its beef neighbor. You need J prime here.
Oh, yeah.
No, that was the question. Why do we need to keep track of the going back stages? So it's only because of this. It's like I don't really need the A prime, B prime, just the J prime. Little bit.
But we need the instruction for where to go after.
Ah, right. You need
Only the B.
only the B. I don't need this. This I don't need. I don't know how to gain from that, but I don't see I need those. It's not like recursive. They are not larger and there are things like this. Just
This came from like log B.
right. Even log, yeah. Even log C or whatever. But yeah, I mean, that's good. That's the point. Yeah, I missed it. I think I knew it once, but like that. Right. So good. Thanks. It's not like if this doesn't appear here, when you say okay, it's not appearing. Just remember it for a second. But there is no second because you go here and do the recursion. So when you get back, if you didn't save it here or somewhere, it doesn't there. It's not there. You need it. So it's not for the good. It's not for any of the things we said. In the third step, you can do another iterative things, and for the square, it's really completely redundant.
When you remember, you define squaring, you define phi as only like the vertex, but then when you came to define zigzag, you said I have to extend the phi
Right.
the previous,
Right.
because you couldn't define zigzag without the previous.
That's true. I need to know who is in the definition. Yeah, good point. Yes. Okay, so I think we should stop here because like we're done.
I didn't have
Ah, that's why I put it here. Yeah. Yeah, that makes sense. Well, okay. So in the next lecture, we'll talk about small bias sets. We start a new topic: pseudo generators and small bias sets.